everyone. Today we will continue to talk about data wrangling. So in today's lecture, we will talk about how to merge two data sets, two data frames. And also we have time, we will talk about how to tidy data using the tidyr package. Okay. All right, let's start. Where are we? Last time we finished the topic about wrangling one table, talk about the 5 verbs plus one group by, right, and also the pipe operator. So today we'll talk about wrangling 2 tables. So data analysis usually involves managing multiple tables, multiple data sets. That is because these tables are called relational tables because it is the relations, not just the individual data sets that are important. Okay, so relations are also very important. And we will continue to use the dplyr package. And in this package, there are 3 families of verbs that work with 2 tables. So 3 groups of functions that can be used to deal with 2 tables. The first group is called mutating joins. And the second one is filtering joins. And the last one is set operations. So mutating joins are used to add new variables to an existing table. So it's kind of like the verb mutate when we used to deal with one table. So that's why it's called mutating join. And the second group, filtering joins. So these are used to filter observations from one table based on whether or not they match an observation in the other table. So filtering joins are used to filter rows or selecting rows. And mutating joins are used to select columns or add columns, add new variables. And last one, set operations. So the functions in this group are similar to those functions we talked earlier in base R. There are some functions that can be used to deal with sets, like for example, union, intersection, and set difference, etc. So there are some parallel functions in dplyr that can be used to combine observations in different data sets as if they are set elements. Right? So basically treat each data set as a set, right? And each observation, each row is one element in a set. So that is the third group, the set elements. So this discussion assumes that we have tidy data, which means all the data sets are clean, and each row is corresponding to one observation, and each column is corresponding to one feature or one variable. All right, so we start with mutating joins. So this join is the most important and most commonly used join family in dplyr. So it first match observations by their keys, okay, key variables, and then copy across variables from one table to the other. So they can be used to add new variables to an existing table, just like the mutating function. All right. There are 4 types of mutating joins: inner join, left join, right join, and full join. We start from the inner join. So we first create 2 toy data frames, toy tables, because using these kind of simple data sets is very clear. Okay, so to make the operations very easy to understand. So the first data set or table is called X, and it has 3 rows and 2 columns, okay? A key column and the value column, value X. So the key column it contains double values, 1, 2, and 3, okay? Kind of like ID. And the second table is called Y. And it also has two columns, a key column and a value Y column, right? Which is also a character. And the 3 rows. Right? Notice that the key values are not exactly the same. Y has 1, 2, 4, and X has 1, 2, 3. Now let's start with inner join. Right? The basic syntax is inner join X, comma Y. X is called the left table, Y is called the right table. And then let's do it. Let's use the pipe operator. Right? X pipe inner join Y. So this is essentially the same with inner join X, Y. Okay. But we just use the pipe syntax. And immediately you see this message is printed. Okay? Joining with by equals join by key. And this key variable is figured out by the function. It will automatically find the common variable in the two data frames. Apparently, in our example, the common variable is the key variable. They have exactly the same column name. So key is used as the key variable that is used for matching, kind of matching purpose. And then this is the result. So see, only the rows with the matching key value are kept in the result. So you see, both of these X and Y data sets have key values 1 and 2. However, the third row, right, the third observation don't have the same key values. So the third row of X and the third row of Y are removed from the result. Only the first two are kept. So this is the most important feature of inner join, right? So any unmatched rows are not included in the result. So of course, by doing so, we will lose some information. We will lose some observations for sure. So this is an inner join. So that's why inner join is not preferred usually because we will lose information. Instead, the most commonly used mutating join is left join. The syntax is left join X, Y. X is the left table. Y is the right table as usual. And if we use a left join, then all of the rows in the left table, namely the X table, will be kept, will be retained in the result. And only rows that have a matching key value in the Y table will be kept. And also variables in Y will be added to X. So let's do a left join for X and Y. X left join Y, join by key as usual because key is the common variable. And then this is the result. So see the entire X table is kept, but only the first two rows of Y values will be added. And a missing value is automatically filled for the Y for the cell when the Y column does not have a value because the Y table does not have key value equals 3. And so a missing value is automatically filled. So this is called a left join. It is good for joining some metadata with some main table. So of course, in this case, the left table is the main table, and Y is used to add some supplementary data, some new variables. This is the left join. The left table will kept complete. And the right join will do a similar job, except that the right table will be complete, will be kept intact in the result. For example, if we do a right join for X and Y, you see all of the values in value y will be kept. So the entire y table is kept in the result. However, the x values, the left table, only rows with matching key values will be kept in the result. And missing value will be filled. So this is a right join. Very similar to left join, just except that the right table will be kept complete. And however, you see, because x is the left table, y is the right table, still variables in y will be added to the right of the resulting table. Okay, so the order of the variables will stay the same, will be the same, even if you do a right join. Okay? Value y will be the last column because it is from the y table to the right table, and it is added later. Okay, we start with the x table. And last one is full join. Full join will include all observations from the two tables, no matter there is a matching key value or not. So let's do a full join. So you see, this is the result. Both the left table and the right table are complete. And missing values are filled if necessary. This is a full join. So if you don't want to lose any information after the join action, then use a full join. So this is the most generous case. And the left, right, and full join together are called outer join. So compare with the inner join. The inner join is by itself. It's by itself. It will delete. So potentially both two tables won't be complete after the join. But the left join, right join, full join will keep at least one table complete. So this is mutating joins. And sometimes, so ideally the key variable, the variable that we use to do the matching job, should contain distinct values, okay, no duplicate keys. However, in practice, it's possible. For example, let's create two new tables, x and y. So you see, x has two rows of with key equals 1, and y also has two rows with key equals 1. So duplicate keys, this means. Then if we do a join, for example, a left join, x left join y, then you see we have a warning message putting out. Detected an unexpected many-to-many relationship between x and y. Okay. So that means many-to-many. Okay. Then the join doesn't know how to do the matching anymore. Okay. Should it be 1 to 1, 2 to 2, or 1 to 2, 2 to 1, etc. All of them are possible. So instead, it will do a Cartesian product of all of the combinations. So eventually, we get the result like this. It will match. Consider each combinations. X1 with Y1, X1 with Y2, X2 with Y1, X2 with Y2. All of the possible cases. So 2 rows times 2 rows, totally 4 combinations. So this is the case when we have duplicate keys. It will create Cartesian products of the matching observations. So now let's take a look at the NYC Flight 13 package. So as I said last time, this package contains information about flight data that departed from New York City in 2013. And there are actually 5 tables in this package, and the flights table is the main table, which contains some the information about each flight. And let's take a look at the data set again, the main data set again. Because this data set is very wide, it has 19 columns. So let's select a few columns and call it flights part and print 3 rows. Departure time, arrival time, carrier, flights, etc. Okay. And if you pay attention to the values, you see in some of the columns, we have some code. For example, the carrier airlines, we have code, and also destination airport, origin airport, and also, yeah. So all of these have some kind of code. It's difficult to interpret and understand. So that's why sometimes we need to add some metadata into the main table to better interpret the columns. Okay. And also take a look at the origin. We know that all of the flights were departed from NYC. But there are 3 airports actually, like JFK, LGA, LaGuardia, and EWR, 3 airports. So take a look at the distribution of the 3 origin airports in NYC. So 3 of them. Just pay attention. Although all of them departed from NYC, New York City, they are from different airports. Now let's take a look at the code book or metadata for the flights data set. So there are actually 4 more tables. The first one is called airlines. This one contains the full carrier name and its abbreviated code. Right? So in the flight data set, the airlines or the carrier there are abbreviated code values for the airlines. But this one provides full carrier name, airline names. And airports. So this one gives information about each airport, geographic information, etc. And then planes. So this one gives information about each plane for the specific flight. Specifically, it has a tail number and some other information. For example, manufacturer year. And the weather. So this one gives hourly weather data for each NYC airport. So this weather data set is only about the origin airport, one of the 3 origin airport. All right, let's take a look at them one by one. First, the airlines data set. 2 columns only. First one is a carrier code. For example, probably you are familiar with UA, AA, like Delta. Right? But some of them might not be very familiar, like the first one, 9E. It stands for Endeavor Air Incorporation, etc. And B6 is JetBlue. Okay? So this one contains carrier code and their full names. And in this data set, apparently the carrier column is a unique identifier, right? Because each airline has a unique carrier code. So in this case, for this data set, this variable carrier can be used as a key variable. For example, when we do matching, when we do merging or join, we can use this as a key variable to do the matching. And the second metadata data frame is airports. So this one contains a few variables about the airports. Right? They may be the origin airports or the destination airports. Right? So the first column is called FAA. So this is the FAA code for each airport. FAA stands for Federal Aviation Administration. That is a unique code for each airport. And then we have the name, latitude, longitude, altitude of each airport, and time zone offset from the GMT time zone, the standard time zone. And DST is daylight saving time zone. Either A equals standard or U unknown. Airports in the US should have standard daylight saving time zone, but international airport may not have this. Okay. And lastly, time zone, the exact time zone. So this is not the same with time zone offset. This is the time zone calculate string. So this is airport. So apparently for this data set, FAA can be used as a key variable because it contains unique values. And next one is planes, information about plane. The first column is tail number, and then year of construction, year of manufacture, and then type, manufacturer, etc. Okay. So for this data frame, which variable is appropriate to be used as a key variable? Anybody? Okay. By our standard, the tail number should be used as a key variable, right? Because it contains unique values. All right, let's move on to the next one, okay, weather. So this one is a little bit more tricky. So it contains hourly weather condition for the origin airports. There are 3 origin airports, okay? So it has 15 columns. Origin, year, month, day, hour. So all of these are used to define the hour of each observation. And then temperature, the EWP, humidity, wind direction, etc. A lot of information. And the last one, time hour, is a combination of the date and hour information for each observation. So for this data frame, to create a key variable, we need multiple columns, apparently, right? Any single column cannot be used to define, to uniquely identify one observation. So this time hour is very close. It contains the date and hour of the observation. However, remember, there are 3 airports in New York City. So you have to identify the airport as well. So to create a key variable, we should combine these 5 columns together, origin, year, month, day, and hour, to create a unique key variable for this data set. Alternatively, we can combine time hour and origin together. Okay. However, this variable is not contained in other data sets, other tables. So technically, it is not usable. Okay, we should still use these 5 to create a key variable to do the matching. All right, so this slide shows you the relationship between or among the 5 tables. Flights is the main table, right? And these arrows shows you how they are connected. For example, airport and flights are connected through this FAA code in the airport data set and origin and destination in the flight data set. So in the airports data set, the FAA code is just called FAA because there is only one column that is about airport code. However, in the flight data set, there for each flight, there is an origin airport and the destination airport. We have to differentiate them. So that's why they have different names. But both of them are FAA code. actually. And planes, definitely we should use tail number to match them, to connect them. For weather, as I said, we have to combine all of these 5 variables to create a unique key variable. So consequently, these 2 tables will be connected using these 5 variables. And lastly, airlines, carrier, the airline. So this is a relationship, okay? And then after we see that, let's use some mutating join functions to add metadata information to the flights data set. Uh, because we know that whenever we use a mutating join, the new variables will be added to the right of the existing table, the left table. Consequently, it's difficult to see the result if your left table is too wide. So that's why let's create a narrower table from the flight data set. We select year to day, our origin, destination, tail number, and carrier from the flight data set and call it flights 2. And then suppose we want to add airline names to the flights data set. We can do this. Flights to pipe left join airlines and save the result in flights 3. And you see automatically this join was by the carrier variable. So this is a common variable of these 2 data sets, flights and airlines. So this is the result, the first 5 rows. Right? So you see this column is added. Right? This is from the right table, the airlines table. Yeah. This is from airlines table. It's added to the right of the table. And controlling how the tables are matched. So notice that so far when we do a join, a mutating join, we didn't specify the key variable that is used to do the matching job, right? So actually dplyr allows multiple ways to specify the matching variable or the key variable. The first option is null. So by equals null. So that is what we did so far. We didn't specify the variable we want to use to do the matching. In this case, dplyr will use all variables that appear in both tables with the same column names, of course. All variables. If there are 2 variables, then it will use 2 variables, okay? So, for example, so the weather data set has all of these, okay? And also the flights data set also have these variables. If we do a left join for flights 2 and weather, then automatically the join will be by all of these 5 variables, right? Because they are all existing in both tables. So then the join is done correctly, actually. Okay. However, this might not be always be the right choice. For example, if we want to join flights 2 with planes, the planes table. Remember in the planes data set, there is a tail number and there is also a column called year. However, the year variable in planes is the manufacturer year of manufacture. Is not the flight year. But in the flight data set, year is 2013. It's very specific. It's the flight of the year of the flight. So although they have the same name, they contain different information. In this case, we must specifically specify the by argument. So by equals tail number only. Otherwise, it will use tail number and year at the same time, and we probably will not get anything, right? And no observation in the result. because there won't be any matching tail number and year. So this is the second option. I specifically specify the by argument, which variable we want to use to do the matching. Okay. And notice that after we do the join, the year columns in the output are disambiguated with a suffix. Okay, so namely, it will keep both the year columns in the result, but it will give a suffix. For year in the left table, it's at year.x. So this is the year from the flights table. And year.y, so this column is from the planes data set, okay? Year of manufacture. So it won't lose any information. But of course, you can change the names using the rename function to make them more meaningful. I give a new name to them. All right, so this is the second option. And sometimes the two tables contain the same information. The two tables have two columns, two variables, which contain the same information. However, they have different names in the two tables. In this case, we need to use this kind of syntax to specify the key variables in the two tables. By equals C parentheses V1 equals V2. Use quote. V1 is the key variable in the left table. V2 is the key variable in the right table. Right? So they have different names, but they contain the same information. We use this to do the matching. For example, we know that in the airports, in the flight data set, there are two columns that contains airport information, destination and origin, both of them, okay? So although they all contain FAA code, they have different names. And in the airport data set, the column is just called FAA, so they have different names. Suppose we want to add the airport information, airport name to the destination airport for each flight in the flight data set. We can do the following. Right? So flights left join airports by equals C, destination equals FAA. So this will add airport names to destination airports. Similarly, if we want to add airport names to the origin airport, we can do this. Let's see the result. So this is corresponding to the first join, left join. So see, for example, Miami information. So this is corresponding to the destination airport. This is the name of the destination airport. And if we add name for the origin airport, so see, for example, this is JFK, right? We match, right? And LaGuardia, we also match, right? So this is a case that the key variables have different names in the two tables. You use this kind of syntax. Oh, this is the last slide of this session. All right, let's move on to continue. We're done with mutating joins. Mutating joins have four types. Inner join, left join, right join, full join. And all of them will add new variables to the left table. And now let's move on to the second and third families of joins. The second one is the filtering joins. Take a look. So filtering joins match observations in the same way as mutating joins. However, it affects the observations, not the variables. So this is very important. It will change the number of rows but it will not add new variables. It will not change the number of columns even after we do a filtering join. There are two types of filtering joins, semi-join and anti-join or anti-join. Semi-join keeps all observations in X that have a match in Y. So X is the main table and it is the focus, right? And we use Y to filter rows of X. So whatever the result is, the rows are from X, right? They are not from Y. And there will be no new variables added from Y, right? And anti-join or anti-join does the opposite. So this one drops all observations in X that have a match in Y. Still, it works on rows in X only. It will not add new variables to X. It will only use Y to filter observations in X. Right? So it does it in the opposite way. It only keeps the unmatching observations. So let's see some examples. So for example, so these semi-joins are useful for matching filtered summary tables back to the original rows. For example, we first find the top 5 most popular destinations in the flights data set. We can use this pipeline to figure it out. Take flights, group by destination, then use a summarize function to calculate the number of observations in each destination airport. Okay? Then sort the result in descending order of n. So then the most popular one will be on the top. Okay? The one with the biggest count will be on the top. And then we use the head function to subset the top 5 and save the result in top 5 DESD. So this is just the summary table we get from the flight data set. So these are the 5 most popular destinations. Alternatively, we can use the following code. So instead of using all of these, we can use the count function, right? Count destination. So it will just automatically count the number of observations in each destination and then sort equals true. So interestingly, by default, it will sort in descending order. And this is the result. Okay. Same result. Right? So this is the summary table. Then we can use it to filter flights that actually went to these top 5 popular destinations. For example, we can do so first let's just use the filter verb we just learned in last lecture. Right? We can do it too. Right? You can do this using this membership operator. Take flights and then pipe filter destination in top 5 destination. So this destination is from the flight data set, okay? And if the destination is in the destination column of the top 5 popular destination, then select that row. And so then we get the result. So we can quickly check the result. So indeed, only these 5 destinations are selected. Only flights that went to these 5 destinations are selected. Right? And the summary statistics should be the same with the previous table. We can also use a semi-join to do it. Take flights and semi-join top 5 destinations. So this is the left table. This is the Y table. In the standard syntax, this is X, this is Y. And then specify the column we use to do the matching job. So bar equals DST. And then, so you can forget about this if you only want to select the flights. And then if you want to furthermore check the result, then add another layer of step. Right? Add pipe count like this. So this is the exact same with this. Okay. So this is how we use semi-join. It is used to use some summary table to filter some observations, filter out some observations. Now anti-join. So this one is used to delete some observations, some rows according to some standard. It will delete observations with matching values in the Y table. For example, we observe that there are some planes don't have a matching tail number in the planes data set. So this one anti-join is used for diagnosing join mismatches. For example, many flights in flights don't have a matching tail number in the planes table. So which means the planes table is not complete. Right? It does not have all of the tail numbers of the flights in the flight data set. So let's try to figure out those flights without the tail number. We can do the following. I take flights, then anti-join with planes. Again, this is the X table, this is the Y table, and by tail number, then count tail number, sort equals true. And this is the result. Right? So it turns out that 712, there are 712, actually there are 722 rows, right? So these many flights don't have a matching tail number in the planes table. That's it. Okay. Not that flights, unique numbers, unique values, and not exactly flights, because each unmatching, mismatched tail number has multiple observations apparently. And the largest category is missing. So many of the flights have missing values in tail number, about 2,500 of them. And then this tail number has this many observations, etc. So anti-join is used to find mismatches in the join. And now we have some toy examples to show the difference and relationship between the two filtering joins. So we first create two tables. Right? The first one has two columns, X and Y, and 4 rows. Right? And the second data frame called DF2 has 3 rows and 2 columns, X and Z. Okay. And now let's first do a semi-join. Take DF1 and then semi-join with DF2 by X. So if we observe these two tables, because these two tables are too simple, it's very easy to eyeball the result. Semi-join, that means only only observations with matching key values will be kept in the result. Right? So only these 2 rows will be kept. Right? So this is the result. So this example shows you exactly how a semi-join does, and also you see this variable z won't be added to the new table, right, to the result. So it will, based on the left table, and the results, all of the rows are from the left table only. The right table, the Y table is only used as a tool to filter observations. And anti-join does the opposite. So we select all of the rows that don't have a matching value in the X column. So in this case, you see 3 and 4 are not contained in the Y table. So these 2 rows will be selected. Okay. Again, both of them are from X. from the table, from the df1 table, not from the df2 table. And the results are complementary. If you union these two sets, you will get the original df1. All right. Exercise, we'll skip those. All right, let's move on to set operations. So this is the last family. There are three basic functions: intersect, union, and set difference. Notice that they have the same name with the base R functions: intersect, union, and set difference. However, pay attention, these functions are from dplyr, so they work on data frames. They work on data sets instead of sets. The base R functions are used to deal with sets or like arrays, like vectors. But both these X and Y are data frames. So the intersect function will return only observations in both X and Y. The union function returns unique observations either in either X or Y or both X and Y. And set difference return observation in X but not Y. So in this case, X and Y are two data sets with the same columns. They should contain similar columns. And the only difference is they contain different observations, different rows. So let's see some examples. We'll create two toy data sets tables. df1 has two rows and two columns, X and Y. And df2 also has two rows and two columns, right? Same variables, X and Y. Right? Then it makes sense to do set operations, right? Otherwise, it doesn't make sense at all. And notice that the first row, the first rows are the same for the two data sets. Right? The second rows are different. Now let's find this intersection using the intersect function. Naturally, the first row will be in the result. The union will contain observations that are in A, in df1, dfb, or in dfb, or df2, or in both. Right? So totally 3 rows. And we follow the convention, which means there won't be any repeated rows in the result when we calculate the union. Only one copy of the overlapping area will be kept in the result. Okay? And set difference. This also works in the same way as the base R function. So again, let's show the two data frames again. So set difference df1, df2 will remove common elements in df1, df2 from df1. So the common elements is the first row, right? First row. So the first row will be removed from df1. So consequently, the second row of df1 will be retained, will be in the result. And if we start with df2, then the common rows will be removed from df2. So consequently, so this row will be left, will be retained in the result. All right. So these are the set operations, set differences. All right. Any questions? If you have no questions, let's move on. So next small topics is data import with readr. So readr is part of tidyverse. It contains some functions that can be used to efficiently read in data sets, also different types of data. So there are some functions. The read_CSV reads comma delimited files. like CSV files. And this one, CSV2, reads semicolon separated files. And TSV reads tab delimited files. So these are the files with separated with tabs. And last one, read underscore delim. So this one can be used to read in any type of files, right? Files with any types of delimiter. So this is the most general one. And so these functions all have similar syntax. We'll focus on read underscore CSV. Let's take a look. Right. So we have a survey.csv file. Right, so this one contains, so if we use this to read in the CSV file and call it survey, automatically some information will be provided. Number of rows, number of columns, and the data types of columns, and some other information. And then if we print out survey, so this is a result. So this is a regular CSV file with column names already included and no, and it starts from the very first row. The very first row contains the column names, so no supplementary information or metadata at the beginning or at the end. Then you can just directly use this code, this type of code without any additional arguments. And so by default, the read underscore CSV reads the first line of the data for column names. And if, for example, there are some description of the data at the beginning of on the top of the spreadsheet or CSV file. For example, there are 3 lines of code, 3 lines of text at the beginning. Then you can choose skip. You can use skip equals n arguments to skip the first few lines. So in our case, we can skip the first 3 rows and then get the correct result. Okay. Sometimes the data set does not have column names. In this case, you need to specifically tell the function that there is no column name. Column names equals false. Then it will start to read. Sorry. It will start to read data from the first row. And automatically it will add column names for you. It will create column names for you. Of course, it will give you this kind of generic names like X1, X2, etc. And later on, you can rename them. So you can rename them later, or you can give a name at the beginning. Right? So you can create column name for yourself when you read in the data set. So this is read underscore CSV, this file, this function. We can also use this function to create a CSV file. So this is very interesting if you wanted to create a toy data set by yourself. So this is a very simple, the basic syntax. Just quote everything together. The first row will be assumed to be the column names, A, B, C, and starting from the second row, you specify the values for each column. The result is like this. Delimiter is comma because we use comma to separate them, and the column names are A, B, C, and the values are just assumed. Okay, so if you type numeric values, it will be assumed to be real numbers. All right. So notice that we also have some parallel functions in base R. For example, we have seen read.csv. So this is also available for us. Why do we have to use a readr function? So that's because readr functions are more efficient. So they are typically much faster, about 10 times faster than base equivalents, right? And they produce tables automatically, uh, and they are more reproducible. So these are the advantages of using readr functions. And also they have more options like read TSV, read CSV2, etc. Okay. It allows different delimiters. And then the last page, the last slide shows you the connection between dplyr and SQL for two table verbs. So for example, inner join, the inner join function in dplyr. In SQL, we can do this: select asterisk from x, join y on x dot a equals y dot a. So suppose the key variable is a. So all of these joins have corresponding SQL code. So basically, the dplyr package is trying to imitate SQL syntax and the way that SQL does query. So all of them are, if you are familiar with SQL, you know that these are the four types of joins. So summing, join, intersection, all of these are available in SQL as well. So consequently, dplyr functions are also very efficient and very effective in dealing with data frames. All right. That's all for dealing with two tables. We talked about three families of functions: mutating joins, filtering joins, and set operations. So they all have their different functionality. All right, we still have about 15 minutes. So let's move on and talk about tidyr, how to tidy data. Because this is a summer class, we have fewer lectures, fewer class time classes than regular semesters, so I have to, yeah, teach faster, a little bit faster. All right, so I will just use the Wrangling webinar, this set of slides. So we'll start from slide 13 and talk all the way to slides about 77. So this part is for tidying data. And this set of slides also contains a summary for Wrangling 1 table, Wrangling 2 tables. It's a very good summary about everything about data wrangling. Of course, it provides some different examples, simpler examples actually. So you can read through all of the slides if you want to do a review. All right, let's start from here. Okay, so we will use this package, data set in this package, right? EDAWR. There are 4 data frames: storms, pollution, cases, and TB. So actually, we won't use the last one today. I will only use the first 3. And take a look at the 3 data frames. Storms, 4 columns. The storm name, wind speed, pressure, air pressure, and date. Okay, so it's a very simple data set. It's sort of in a tidy format already. The second one is cases. It's called cases. So apparently this is a contingency table. It contains some summary data If we decompose the information into three parts, it contains country information, and year information, and some counts in the table, right? And lastly, the pollution data set. It looks quite tidy. Um, it has 6 rows and 3 columns. Okay. Now let's decompose the information in a special way. City, um, amount of large particles, and amount of small particles. Right? And the reason that we summarize the data frame in this way is because we will try to rearrange or transform the data set into a different way. Okay? So let's see. We can actually create a new variable using existing variables. For example, we create a variable called ratio, which is equal to pressure divided by wind. So it is definitely possible. And then let's see what is the definition of tidy data. Very simple. Each variable is saved in its own column, and each observation is saved in its own row. And then each type of observation stored in a single table. Here is storm. So a table is very kind of specific. Right? It contains information about a specific type of information. So in this part, we will talk about this package, tidyr. Okay? This is also included in tidyverse. It has 4 functions. Let's talk about the first two. First group, gather and spread. So these 2 functions are used to reshape the layout of our table. If you want to take a look at the documentation of these 2 functions, you can load the package and then type question mark gather or question mark spread. So let's first take a look at this cases table again. It has 3 pieces of information: country, year, and count. Okay, but apparently this is not in a tidy format because each row contains 3 years of information of a country. So it's not that tidy. Suppose we want to create a new data frame with 3 variables: country, year, and count. Okay, so 3 of them separately. Not in this format anymore, with 3 columns: country, year, and count. Then what should we do? So first list the 3 columns: country, year, and count, call it N. Then let's see how to convert the each cell to this to each row. Okay, so actually, just each cell in the table will become a row. Okay? Of course, together with the row name and column name. The first observation will be corresponding to France in year 2011 and the count. Similarly, the second country, third country, US in 2011. And then move on to the second column. So totally we have 9 cells. There are 9 cells in the table. So there will be 9 rows in the new table. So this is called gather. Why? Because we gather the information from the 3 columns, 2011, 2012, 2013. Gather them together and put them in 2 columns, year and N. Okay. So in this case, notice that the column names 2011, 2012, 2013 are used to create a new key variable called year. Okay? So the column names become values in the key column. Okay? And the cells, the entries, become the third column, the values of the third column called n. Notice that both of these columns, year and name, did not exist in the original table. So we need to create them by ourselves. So the syntax for the previous example is this: gather cases. This is the data frame name, right? Data frame we want to reshape. And then the new variable that contains the key values. So name of the new key column. The values of this one are the original column names. And then the new variable we created to contain the cells, right, the entries in the table. The new value column. So this is a key. This is a value column. Key value column. And lastly, the names or numeric indexes of columns to collapse. Oops. So 2, 2, 4. You see 2, 3, 4. In the cases data set, we collapsed the second, third, and fourth columns together and create these two columns. So this is how the gather function works. So this is a summary. The two new variables, you should put them in this order: key, new key column, new value column, and then a list of columns to collapse. And then let's move on to the second example, pollution. So the pollution data set contains information like the amount of large particles and small particles in 3 cities. Suppose we want to reshape this pollution data frame to a new data frame with 3 columns: city, large, and small. City, large and small are apparently new columns, but these two values, the column names, are originally values of the size column, right? So in this case, let's see how to reshape it. Imagine how we can reshape it. 3 columns, and then the first row will become this part of the first observation, and the second row become the second number in the first observation for new row. So basically, we want to create one observation for each city, collapse it. So originally we have 2 rows for each city. So now we have 1 row for each city. In order to do this, we use spread. Why? Because we actually spread the table. Although this is a special case because originally we have 3 columns and now we still have 3 columns. That is only because there are only 2 levels in the size data set, in the size column. Imagine if there is 1 additional category, which is median, okay? Then naturally we will have 1 more column, which is large, medium, small. So totally it will become a data frame with 4 columns. So you essentially spread the original column to a wider one, original data set to a wider one. So that's why it's called spread. It really depends on how many levels are contained in the key variable. So let's see. So the column that we use to create the new column names is called the key column or key variable. So we see we use the levels or values of these variables to create column names. We create new values, new variables. And then the column that contains the cell entries are called the value column. So notice that in this case, both of the 2 variables exist in the original data set. So this is syntax: spread the data frame pollution, and then specify the key column, namely the column that we use the values to create new variables. Okay. In the pollution data set, size is the key column. Okay. And similarly, we specify the value column, which contains the cell entries. So in the pollution data set, amount is the value column. So notice that in this case, you don't need to use quote anymore because they both exist in the pollution data set already. So this is how it works. The value of size becomes column names. The values of amount become cell entries. So this spread. Apparently, spread and gather work in exactly the opposite ways, right? Spread will make a table wider theoretically, and gather will make a table narrower theoretically. All right. The last two functions in tidyr we will talk about are the unite and separate functions. So these are used to combine columns together or separate columns, split columns. For example, in the storms data set, the last column, date, contains three pieces of information, the year, month, and day. Suppose we want to create a column for each piece. Namely, we create three new variables, year, month, and day. We can do the following. Right? Separate, specify the data frame, storms, and then the variable we want to separate. Right? And then a vector of new column names, namely year, month, and day. Use quote. And then lastly, specify the separator that were used in the original values. The separator was hyphen, so we use quote hyphen. And then the separate function knows how to separate the values. Right? So the hyphen is served as a separate delimiter. Right? And then we get this. And notice that in storms 2, the date variable is gone. It is replaced by these three columns. So this is separate. So very intuitive. So it will not change the number of rows. It will only change the number of columns. Unite works in the opposite direction. For example, let's take storms. And then we want to create a new variable called date, which is a combination of the three variables, year, month, and day. So basically, you first specify the new variable, and a list of variables you want to unite together. And then lastly, specify the separator. If we want to transform it exactly back to the storms data set, we can use the same separator hyphen. And then this is the result. I will create a new variable called date, which unites the three pieces of information together. So now in the storms data set, you see year, month, and day are gone, and only date exists in the result. So this is the unite function. You have the option, you can change the separator. For example, you can change it to slash or period or space. All of them will work. So it's quite flexible. All right, I think, yeah, so this is a summary of the four functions. So gather will make observations from variables. Spread will make variables from observations of one column. split and merge columns with unite and separate. All right, we're done. Great. Next time we'll talk about how to impute missing values using R packages, which is